The thing that I wanted to tell you about today is work which is done in collaboration with Stefano Lanza, Luca Martucci, and Irene Valenzuela. And it's based on a paper that appeared a few months ago. And wait, okay, great. You're going to excuse me, but I don't see here. Very good. Yeah, very good. That appeared a few months ago, and one that should be appearing soon, hopefully. So, okay. So, sorry, I just have a little bit of trouble because I don't know how to point things. Can anyone help me?
Maybe you get out of full screen mode, you may be able to use your pointer.
Yeah, okay.
Yeah, so now I can see your pointer. So maybe don't use the full screen mode.
Oh, that's very sad. Okay. Okay. Okay, let's do it like this. All right. So especially the talk of Daniel and Timo, let me start with a brief sketch of how the story relevant for this talk goes. And this story starts with the Swampland distance conjecture. Of course, I will be super sketchy because this is not a very short story. There will be lots of things going on in this sense. And I will just be mentioning those papers that are more relevant for the things I'm going to say. So apologies about that if anyone is not represented properly. So,
Bob, sorry, but if you wish, you can, I think in preferences of Keynote, you can put that your click, I mean, that the mouse should appear if you want to try super quick.
Okay, yes.
Otherwise, just continue this way.
No, but where? Okay. I show, yes.
Show preferences, show pointer when using mouse.
Here it is. Okay, thanks a lot. Okay, let's try this. Okay, thank you. So as I was saying, so the story starts with the Swampland. This is conjecture. You have already seen about it in the presentation of Timo and Daniel. And Bob, this is a conjecture that was proposed based on some examples, some examples that we saw in string compactifications, but that has managed to capture a lot of physics and a lot of very important physics that we see when we do a string theory, right? In very complicated setups. So essentially it tells you that when you go along a very large distance, there is going to come some tower of states that are going to spoil your effective field theory as you used to work with it. And in some sense, it gives you a maximal radius of your weakly coupled region, no? Because actually these things happen very often when we are in a weakly coupled region. We say, okay, we can do perturbative physics here. I want to do some, I don't know, models of large string inflation and go over large excursions. And then all of a sudden, this conjecture, what it tells you is that the maximal size that you are allowed to think of in terms of your effective field theory is given by this quantity. So we see exponential decay in proper distance that is characterized by some real positive number lambda. And well, the conjecture doesn't tell you what this value is, and it doesn't tell you what is the nature of this tower. But as I said, given the amount of activity that this conjecture has created, especially by looking at examples in string theory, people have come up with revised versions that, well, for instance, postulate that this quantity should be of order 1, or even propose what the nature of this tower of states should be, like the emergent string conjecture that we just saw review a few hours ago. So in the emergent strings conjecture, we either we are only allowed to have a tower of Kaluza-Klein states or a tower that reproduces the spectrum of a tensionless, well, asymptotically tensionless critical string, right? Good. Now, as I said, typically how the progress has been made is by looking at the specific classes of compactifications and checking whether the conjecture is true or not. So far, it has passed all the tests. And you have seen how the machinery goes and how intricate the geometry can be in the first talk of this conference. The things become more complicated as you lower the supersymmetries, as we are very well used to. But I mean, there is so far a pretty amount of technology that tells us how to deal with this problem and how to look at things and how to make a good idea of whether, well, the tower of state is going to come from and what is going to happen. In this talk, the thing that I will have in mind is theories with 4 supercharges in 4 dimensions. Our favorite n equals 1, which has the additional complication that you have a potential, just like the example that we just saw in the last talk. Now, having a potential is an interesting problem because, strictly speaking, the Swampland conjecture was formulated when you have a strict moduli, so moduli space, so no potential, no so whatever. But of course, what we expect is that if we can sit ourselves in some scale at which this scale of the potentials can be neglected, then we should be able to apply the same philosophy. Or if you want differently, the scalar potential maybe will restrict what your moduli space is or your field space is, because at some point the energy of the potential will just tell you, okay, I go at the same level of the cutoff of your EFT. But if it still leaves a large region, in this large region of field space in which all masses and energy of the potential can be neglected, you should be able to see if there is some effect like the one that the Swampland distance conjecture predicts. And this is more or less what we expect because, well, I mean, this is how we build things in a string theory, right? And we start with some moduli space, we add some ingredient like fluxes, like in the previous talk, and then, well, we get a bunch of vacuum. Good. So here. So in this talk, the idea is to take a different perspective. If you want, for instance, to compare it to the 2 previous talks, instead of taking a string compactification, squeezing all the geometry and all the data out of it and getting the 4-dimensional picture or the lower dimensional picture out of it, what I'm going to try to do is to look at the Swampland distance conjecture from the perspective of effective field theory. So, and then at the end, when I try to define and analyze and look at things from the viewpoint of an effective field theory, I am going to try to connect with all this work that has been done from the viewpoint of the compactification. So what is this EFT viewpoint? This is also not new. Essentially is try to realize this large distance or even the infinite distance trajectory in terms of EFT objects. And you can have EFT objects that are described by some solution in space-time, and this solution realizes the large distances. So basically the fields flow along the solution. So again, this is not new. This has been proposed even in the context of Swampland conjecture. Here, the novelty is I'm going to look at these objects that are 1/2 BPS in 4-dimensional compactifications with 4-dimensional EFT with minimal supersymmetry. And this means that I will look in at the strings and membranes, because this will be my 1/2 BPS objects. And by construction, this guy will have a large back reaction that will make make the fields flow a lot. So in particular, the object that will be the star here in this talk are the 4-dimensional strings. Not all of them, a particular kind of them. And to see which kind, let me focus on a well-known example. It's not new at all. I mean, it's probably older than some of the people attending this conference, that was put forward by Green et al. Okay, And this example, this very well classical example already tells you how a string can connect with infinite distance, which is going to be the message to take home from this talk. So I'm going to consider the setup of Green et al. And this basically is a complex scalar field with a fourth effective action of the stone coupled to gravity and with the moduli space metric of axiodilaton, or complexified Kähler modulus that comes from a torus. So very, very, very simple. You get this sort of equation of motion, which is what the author did, and then we realize that the profile for this complexified Kähler modulus, sorry, for this axiodilaton or complexified field is a holomorphic one. And what you do in order to describe the solution is you take a transfer coordinate to this cosmic string and you map it to the fundamental domain of this complex field, so to the model space. Well, the simplest solution is the J function. I mean, many of you know about it. The ingredient that is important for this talk is some very well-known ingredient, which is that the spatial infinity, what we recover is this logarithmic profile for the complex field. And what this is a trajectory in field space that, well, as you go along spatial infinity, you also go to an infinite distance limit through an infinite distance limit in the modular space of the complex field. Okay, so this is like the main intuition that is behind the beginning of the strategy that I'm going to follow. So imagine, for instance, that now I am in a Pi2B compactification, and I have a four-dimensional space times a Calabi-Yau or six-dimensional space, whatever, and I wrap a D7. I wrap a D7 brane on the Calabi-Yau, and I see a string in 4 dimensions. Well, the back reaction of this D7 brane is going to be precisely as the kind of things that we were talking about. The only difference is that the infinite distance path toward weak coupling towards tau going to I infinity is going to appear when I approach the core of the string, and this could be anywhere, not at spatial infinity. So if the string is placed at Z0 in the transverse space, then as I approach it, I will see this logarithmic profile, and what my background will realize is an infinite distance path. Okay. Moreover, what happens in this region is that the axiodilaton goes to a zero coupling, towards the zero coupling region, and the axionic shift symmetry on the axion becomes exact. Is only broken by d-1 instanton effects, but when I approach this zero coupling region, they become negligible. So the idea is to see, well, what happens with the physics of this solution. This patch of the solution, not the full cosmic string, but this patch that contains the infinite distance ingredient of the solution from the EFT viewpoint. And the first step is to extract the essential features out of the examples and generalize it for the EFT to have a global picture. So what are the key ingredients that we saw? Well, the first ingredient that this is a fundamental object. So these membranes in type 2B, we just characterize in terms of some localized operator. And when we do dimensional reaction to 4D, this is not going to change. We are going to see a string, a 4-dimensional string, that it comes with an action of this form, a localized surface operator. As such, well, just like these membranes, we will not be able to resolve it in the effective field theory, which means that the tension associated to the string has to be bigger than the cutoff square of the EFT, and well, smaller than the Planck mass. I mean, this is something that you can ask for your objects. Also, we did it in the previous paper for membranes. And when you try to understand what this means, well, on the one hand, the tension being bigger than lambda to the appropriate power means that the oscillation modes are not going to be visible. So it's really a localized object with no oscillating structure or anything like that. And then on the other hand, this upper bound means that when you compute the back reaction, you are not going to induce gradients that are going to take you away from your EFT regimes. You are not going to induce very bumpy regimes that you cannot understand in terms of an EFT with a cut of lambda. So this is the kind of things that we are going to look at. And also, we are going to demand the other ingredient that we see in the distal membrane that will recover this exact axionic shift symmetry, the more exact and the more we approach the core of the string. So essentially, we are going to look for, well, axionic fundamental strings. And when we are in 4-dimensional supersymmetric theories, we are either going to ask them to be 1/2 EPS. So we give these guys a name because otherwise, sorry, I would be saying axionic fundamental strings forever, and they will take a lot of time, this talk, but we call them EFT strings, also because they are well behaved for the back reaction and so on, and we can treat them in a perturbative limit pretty good. And basically these guys are, if you want, a string solution that realize, that describe a flow, a solution along a perturbative region with a perturbative axionic symmetry, and such that the non-perturbative effects, which are the only ones that can break the symmetry, are suppressed. So to good extent, we have a concept of an axion along the solution, and we can do a lot of, well, a lot of machinery to understand what the physics is. So what we see when we impose this condition is, just like for the distal membrane case, a logarithmic back reaction for the model line. Now, maybe you will have many axions, many axionic partners, and so on. So you will have a more complicated things, but the essential ingredient of logarithmic back reaction is the same. This already implements what the behavior on the axion is, a monodromy, okay? That defines what the charges, the discrete charges of the string are. And then as axion that, well, as you approach Z going to Z0, no, sorry, Z going to 0, I'm going to place the string at the origin for simplicity, will flow to some infinite value, okay? And in this limit, because the non-perturbative corrections are going to be of this sort, the PPS non-perturbative corrections are going to be of this sort, then this thing will flow, and by assumption, this is suppressed. So the only thing that can happen, if my assumption is true, it is goes to 0, and we realize an exact fundamental axionic symmetry. So essentially, with this profile and this assumption, anything that can break the axionic shift symmetry should go to 0. And then the fundamental axionic symmetry becomes exact. And as in many other works, like for instance, this paper of Macris, then what you expect is that this thing is located at some point of infinite distance in moduli space. Because otherwise you will be realizing this exact fundamental axionic symmetry in some perfectly random place in moduli space that you could access via some random process, and well, you will be going against this no global symmetry conjecture that we all know and love. So, so that's why these guys are maps. You can see them as maps from a disk. Let's start with a solution at some definite radius, and let's flow towards the core of the string. You can see them as maps from the disk to the moduli space, and the center of the disk is mapped to an infinite distance point. So it's a perfect setup to probe from an EFT perspective what's going on with the Swampland distance conjecture and all the friends of the conjecture. So, so for instance, something that we can still look from the 4-dimensional viewpoint is analyze this flow. If I parameterize this in this way, one can see that the field space excursion along this flow is characterized by the integral of the physical charge of the string defined in this way. So this is the metric based on a Keller potential, and the physical charge is just by contracting the charges, the contact charges with this metric. And of course, what we expect, we are having a weakly coupled string, is that the charge goes to 0, and this parameter flows all the way to infinity. Otherwise, realizing an infinite distance limit is going to be very impossible. Okay. So this is how we are going to see how the distance becomes infinity, and something that we are going also to see when we look at the tension of the string, and here the tension I associated to the energy stored in a disk of radius r. How the tension as we go along this flow decreases. Okay, basically I'm decreasing the radius and the tension decreases as this. So essentially what I'm describing along my flow is a solution in which these parameters describing the string, the physical charge and the tension decrease monotonically. Okay. Now, if I assume that I have the weak gravity conjecture is saturated is for this string, as I should, well, is a BPS object after all, with some extremality factor gamma in here, then the only sensible solution is the one in which the charge decreases like this parameter sigma to the -1. And when I integrate it based on this definition, then I'm going to get a Keller potential that that flows logarithmically toward this infinite distance point. And well, I mean, it's not that I can tell you what the full Keller potential is out of this one, but for sure, all the Keller potentials that we are used to in string theory are Wikitus. And okay, I haven't seen so far a reason why they are like that, but I mean, they are over and over satisfy this condition, because what we typically have is a Keller potential that is minus log of some polynomial on the section. This is an asymptotic behavior, of course, when we go away from this highly perturbative axionic region, then we will have some dependence coming on the axioms, but near axionic regions in which the axionic symmetry is preserved perturbatively, we always see in string theory things of this sort. Okay, so there is one important point that is crucial to understand what this project is about, is that this profile that I just wrote down, which is nothing but a glorified version of the Green et al. Profile when you approach the this tau going to I infinity. This profile is not what the effective field theory sees. You don't see this. You see some version. You see some approximation to this profile because you have a finite cutoff, and the Fourier modes that can appear in your theory are only up to this finite cutoff. So you will, if you decompose this profile in Fourier modes, then what you will see is the components of the Fourier modes that go all the way up to lambda, but not beyond that. No. So essentially, the flow stops. I mean, this never stops. But the actual flow that you see in your effective field theory stops at some distance that is, roughly speaking, 1 over lambda. And then what happens is that when you put yourself at this distance 1 over lambda, you don't see any flow. The flow has stopped. So all the energy that appears in the system is because of the localized operator that you use to describe your string. So the whole energy is the number that appears in your string action, so what we typically associate with the tension. And that's why essentially we associate this number, this tension, with the energy that you have at with the tension that you have at some energy lambda. Okay. So so if you want to know what the tension of your string at some energy lambda, you just compute the energy of the flow on a disk of radius 1 over lambda, and that's the answer. And basically what the flow does in this sense is to describe an RG flow of couplings that you see as you go away from the string core. So you start at some point, then you go away from it, and what you are seeing is how the tension, the normalization group action on the tension go into the IR. This is exactly the same philosophy that we use to interpret brain-back reaction in terms of RG flows that we only apply here. The only thing that we do here, the difference is we do it below the Klein scale and at the EFT running of the scales. So where you get out of this observation is that the interesting behavior for the Swampland distance conjecture is one, the behavior that appears at very small disk, because this is when you approach the infinite distance, okay? And in terms of RG flow, is the behavior that appears in the ultraviolet, very close to the EFT cutoff. The higher you go, the closer you are describing the physics of large distances. Okay. So this is actually very nice because well, this tells you that you may modify your theory in the IR, and everything that I'm going to tell you is independent of that. So I can break supersymmetry in the IR. I can even give mass to the fields that are flowing. But if this happens at this scale, and I am looking at the tension of my string at this scale, or at radii that has to do with this scale, all these effects will be irrelevant. And of course, if the potential is in here, no, because I will be distorting my string solution by a large amount, and this will the logarithmic profile that I was telling you will not be true. But if I'm doing it here, this will happen at wavelengths much larger than the logarithmic string profile, and everything that we derive from this in this work will be untouched. Also, it already hints you why there should be some sort of EFT breakdown when you go along large distances, because as I told you, when you increase the UV, you go along large distances, which means that the tension goes to 0. And then the cutoff, the EFT cutoff, goes up. So at some point, these two scales will cross, and then you will have this this fundamental axionic string that has an scale below the cutoff, and then you expect something dramatic to happen. Okay, at least what you expect is that you will start seeing the some oscillation modes of the strings, and then the semi-classical description that you're used to will have to be changed or destroyed or whatever. Good. So so this is the pure EFT viewpoint. Of course, at some point we just want to check it, how it works with explicit examples, and see what else we see, or if everything works well or not. So, well, we look at different examples. So perhaps the clearest one is the heterotic compactifications. So we place ourselves at large volume and weak coupling, and we consider the infinite distance limit that correspond to partial or total decompactification, or going to zero coupling, things like that, things that we are very well acquainted with. So in terms of the 4-dimensional objects that we will have a bunch of BPS strings, like the fundamental string or an NS5 brane wrapped on an effective divisor. And we will also have the BPS instantons breaking the associated shift symmetries, like NS5 brane on the full Calabi-Yau, or fundamental strings, bullshit instantons on effective curves. No? So we will, in practice, what we do is we characterize this spectrum of BPS objects in terms of cones, discrete cones. And then there's a nice interplay between our this perturbative axionics region and what these cones are. The first thing that one learns is that not all the charges that appear here, not all the effective divisors are what we were calling EFT strings, because we need that the pairing between the strings and all these instantons is positive. Otherwise, there will be some instanton that when you go along the string flow will become super relevant, and it will hardly break the, it will largely break the axionic shift symmetry. You will not be a weak coupling, and everything will go to hell. So essentially, what you need is that some strings that that are not only effective, but also they correspond to NEF devices. I mean, you need to wrap NS5 brane from NEF devices. And this actually, this is a discrete version of your moduli space, or the direction on your moduli space that describe of these asymptotic limits, which are the 4-dimensional dilaton and the Keller cone. No, I mean, so you can see that this is a discretized version of the naive moduli space that you would have started with when you look at this example. Actually, funny enough, one can take this definition in terms of a positivity of pairing, which is nothing but an intersection number, and relate this story to a very analogous story that has to do with strings in 5 dimensions and the notion of supergravity strings that was put forward in this paper of Katz et al. And actually, in our setup, there is a bunch of mathematical conjectures assuming here that makes physics sensible. The same thing happens here. So we, for instance, we need that all NEF divisors emit an effective representative for things to make sense from the EFT viewpoint. So there is an interesting relation here. So, okay, we look at several examples. I'm not going to go one by one, so you will hate me forever, but let me just try to describe the general features that we see when we look not only in heterotic, but type 2A, type 2B, EFT, blah, blah, blah. So we have that the EFT strings, essentially, in the way we have defined it, they encode all the possible directions that you would think of in which you can realize this infinite distance in a perturbative patch, like large volume with token. Then the charges, I mean, in a sense, they generate these flows, and they say that these charges are a discretized version of what you would call this axionic cone, like the Keller cone, for instance. Along each flow, the string tension that generates vanishes asymptotically. And then, well, we have a Keller potential. This is based on string examples that look like this. And then one can go and classify the flows based on the asymptotics of the Keller potential, or in terms of string physics, the number of EFT strings whose tension vanished in a limit, which can be one or can be more than one. Okay, so essentially this physical data recasted in terms of a string encodes the asymptotics that are here, which are encoded in this polynomial. So it's a way of repackaging the information. And in this sense, actually, all the work that has been done in the classification of Calabi-Yau limits appear in compactifications like heterotic in Calabi-Yau. This story of Thomas of SL2, or the classification of Timo et al. Well, it appears in here, and it just recast in a new object, which is the 4-dimensional string. Good. So so because of that, because of this universality and this one-to-one correspondence of asymptotic limits of infinite distance and string charges that we observe in the examples, we proposed already in the previous paper, but now with more glory and detail, what we call the distant axionic string conjecture, saying that any infinite distant limit of an EFT consistent with quantum gravity can be realized as an EFT string flow. Okay. So what this means is that any infinite distance point will be related with an axionic shift symmetry. As I said, well, because the string becomes tensionless along these limits, at least one becomes tensionless, maybe more. You see, you already see that something should happen, no? What happens is not in the conjecture. Okay, so in this sense, we are almost so far as vague as the original conjecture, but in fact, we are not saying that the EFT will break down because you have a tensionless string. Something could happen before. So you could have some other tower that is a lower scale compared to the string tension, and then, well, that's what triggers the EFT breakdown in the sense that the Swampland conjecture predicts. But what we also observe is that if it's not the string tension, if it's not the string itself creating havoc and breaking the EFT, the scale at which the EFT is broken is tied up with the string tension via this relation. So this is M star represents like the Swampland distance conjecture tower of a state scale that goes down exponentially. And this is a string tension. So because this goes to 0, well, you can have 1, or you can have Q bigger than 1. For Q equals to 1, they will be of the same order. For Q bigger than 1, this will go there before, and this will be the guy, whatever it is, we also don't specify what it is, that will break the EFT. Good. So a first check of this idea is to go back for n equals 2 examples, which has been looked at in all glory and detail, and where somehow this whole story of revamping the Swampland distance conjecture appear. And look what happens in there. So for instance, we can go to the vector multiplex model space of Calabi-Yau compactifications. And
Fernando,
well,
how much more time do you think you need?
oh my God, 5 minutes? I rush. Okay. I'm over
Okay.
time already?
Yes, I think so. I'm afraid, yes.
Okay, I will rush. So you can divide. I mean, let's follow the emergent distance conjecture, and let's classify the limits in two different ways. One, they can be emergent string limits, or they can be the compactification limits. If they are emergent string limits, then well, they say that we were saying is trivially satisfied because the axionic string correspond to the critical emergent string. And if not, well, we already see that there is some string there because, as was Thomas explained to us, you have this sort of asymptotics for the periods. And when you plug them into the Kerr potential, you are going to see an axionic shift symmetry, like we were saying. So just by looking at which axionic shift symmetry it is and what is the monodromy that appears on the periods, you can already guess what your string charges are. Okay, and okay, this is particularly clear in type 2A models where this would be some NS5 frame wrap in some devices. So the same thing can go for hypermultiplet limits, but this is less understood, so let me skip it. What the two things that I really would like to tell you is the interplay with other conjectures. So the first one is the interplay with the weak gravity conjecture. So one can essentially show that this conjecture that I presented, if you combine it with the weak gravity conjecture, you get the Swampland distance conjecture for free. So this is, okay, this is a little bit late, you're all tired, but this is basically one line computation in which you compute the distance of the flow. And the thing that you use is this relation between the derivative of the tension and the charge, and then assume the weak gravity conjecture in the same non-saturated but the inequality. And then you use the relation between the breaking of the EFT cutoff scale in order to express this parameter lambda in terms of two things. One is the extremality factor of the string, and the second one is this number Q that appear in the second part of the conjecture. And then finally, you use the first part of the conjecture to say that all limits are of this sort, so this should be general. Okay. So the second observation is a nice marriage between this distance axionic string conjecture and the emergent string conjecture. I mean, they are not one showing each other, but they are complementary in the sense that if you have this integer number that is equal to 1, as I said, you have that the emergent string is the EFT string, and we have checked that in all the examples that we look at, there was a unique when this happened, there was a unique EFT becoming tensionless. You can have Q bigger than 1, and then what we check in split examples is that you have a Kaluza-Klein like tower of states that were breaking the EFT. And then what we didn't find for any example is that this integer could be bigger than 3. So well, I mean, this is something that we look at the different corners. One can do the exercise in the typical supergravity regimes that we're used to, and you basically get this picture. This is, of course, by inspection. So so one last statement, sorry, so it has to do with the curvature at infinity. That was one on the conjectures that appear in your paper. So we cannot show that. Actually what we see is that in the more tricky flows, which what we call the flows in which several EFT strings become tensionless, we don't find that the scalar curvature at infinity is non-positive. But what we do find by construction is that there is a holomorphic disk that you map into the moduli space. And because of that, and because of the kind of asymptotics that you get for the Kerr potential, and the fact that there is infinite distance and so on, this holomorphic sectional curvature in n equals 1 Kerr moduli spaces will be non-positive. Okay, so will be So this is a much weaker condition than saying that the curvature in infinity is non-positive, but it goes along these lines. And well, that's essentially my conclusions. Sorry about the delay. The basic idea is that we try to understand what the Swampland distance conjecture means from the EFT viewpoint. And in terms of EFT objects, and here what is relevant for us is the four-dimensional strings. Of course, everything that I have said is only for 4 dimensions. The other dimensions, well, you should have to repeat the exercise or generalize the picture that we have done. But in this context of 4 dimensions, we come up with this distance and extreme conjecture that tries to capture the phases that happen here. And that's it. Thank you very much. I'm sorry for the delay.
Thank you, Fernando. So we are a little bit late, and people might want to leave, but we can still take maybe a couple of questions, and then if people have more questions, we can go after the formal proceeding. So Miguel is raising a hand, please.
Yeah, just a very quick question. One could think that the standard model is kind of like a weak coupling, right? Because it's 137. Have you thought what kind of implications would the distant action string conjecture? What can you say about the standard model, or what would you say? Will you be predicting a QCD action or something like this?
So, you wanna treat a QCD action like a fundamental action symmetry?
I don't know. I was just asking in general.
I mean, to be honest, no, because everything that we have thought of is in, let's sort of say, the closed string sector. Like, I mean, we haven't thought about what happens when you have moduli spaces that realize Gates theories in 4 dimension and involving things like open string field directions and things like that.
Okay.
So I would first try to generalize our setup to those settings before trying to say anything as general. But I mean, if you tell me, no, look, this guy is a fundamental action, I could try to apply what we have done, yes.
Okay, thanks.
Okay, Jakob, you have a question.
Hi, Fernando, thanks for a nice talk. You mentioned this thing that not all string charges are what you call EFT strings, because for some values, some sections run to strong coupling instead of weak coupling, right? Have you thought a little bit in the orthogonal direction about what these strings are? Because so we wrote a paper recently where, for instance, which was about monogamy defects in 6D, but you can just map this to 4 dimensions by compactifying. So, for instance, the D7 brane wrapped on K3 times G2 should not be a fundamental string. It's a bound state, and you can tell that it's a bound set of 2 things. Both have a monogamy that squares to 1. Do you know something similar happens for NS5 branes wrapped on devices outside of the NEF cone?
Well, I don't for sure I don't have the big picture, because this is a very complicated thing. And I have to say that in this project, when we impose the weak coupling EFT string, I mean, many things simplify, and when we remove one of these assumptions, things became Hale. So this is something that prevents you to go beyond that. But naively, what I would expect is the same sort of intuition that what we have when we connect F theory solutions to Cyber-Witten and things like that. The same thing that you were saying, bounded states, strong coupling in directions that become bounded states and similar. But I don't have the big picture. But yeah, I mean, everything smells like Cyber-Witten before or after.
Thanks.
Okay. Any other questions? Any announcement from the organizers?